Hello, Arshan. How are you?
Hello, good afternoon. I'm
Good
fine.
afternoon. Thank you for joining us. And Arshan's going to give us a presentation on inkjet printing for applications with small size features. So, as always, I'll hand over the stage to him, and then I'll come back at the end to take your questions. Over to you. Good luck.
Thank you. Thanks for your introduction. Thanks for joining the presentation. As mentioned, I would like to take you on the journey towards smaller feature sizes and the role which we foresee for inkjet printing on this journey. Let me give a bit of introduction, starting with the company which I'm representing. Our company, Do Micro, is a high-tech SME from the Eindhoven area, which is very much rooted in the inkjet printing experience and technology. What we typically do is we provide engineering services to customers in early stages of product development. Think about making a demonstrator of something very innovative with printed electronics, or about, for example, contract research and development. We do that for a lot of application areas like automotive, where, for example, inmold is a big theme at the moment. We have recent experience in healthcare with microfluidics devices, where small interconnections were needed. An important one always is wearables, wearable IoT devices, which you can take with you, which report about lots of parameters to be measured. And certainly semicon is a big one as well. With, for example, the assembly of chips with very fine pitches. Having said that we are an engineering company with lots of services in the product development range, it's important to notice that, excuse me, that we also have a laboratory available which can support us with making various demonstrators and prototypes. We, of course, have a laboratory with inkjet printers because that's the core of the company, the background in inkjet printing. We have two LP50 printers from the company SÜSS Microtech, which you can show on the left hand of this picture over here. We have analysis equipment in the clean room. On the right of the picture here is a microscope, a Keyence optical microscope, which can be used for inspection of the products we have made. And also important is that we have a lab for system integration and for electronical testing outside the clean room. Not shown on the pictures, but also very important, is that there are facilities for curing the samples that are made. We can do thermal curing, we have laser curing equipment, we have a fine placer for putting the components in a very precise way on the substrate, and in that way we can make prototypes a reality. Talking about small feature sizes, where are these important? Simply speaking, the answer is almost everywhere. Obvious examples, which are highlighted here on the left-hand side, are the semicon industry, with the chips getting more complex by the day almost, and where the pitches can be very small and put a lot of challenges on the integration in the circuitry. Automotive is a big one, thinking, for example, about inmold applications, smart glass applications, where small features are needed, for example, for making bendable substrates, bendable products that can be integrated in a curved surface. The solar industry, where parameters like transparency and invisibility of the interconnections are dominating, is a big one. Wireless IoT, wearable devices do play a role, and certainly also the healthcare industry, in particular the microfluidics area, where small connections are to be made. What is the need which is coming from these applications? To put it simply, it's a lot about adding as much as possible functionality in as small a space as possible. The typical targets we are talking about in the context of this presentation are that we should offer heights on flexible substrates up to about 100 microns at most. At the same time, we also need to offer fine pitches, for example, because of the very complex chips we are talking about, with pitches, let's say, in the area down to about 100 microns. In the picture below, we see an example of a controller chip which is integrated on a flexible substrate all the way with inkjet printing. Later, of course, more backgrounds about how exactly that has been done. Talking about small feature sizes and the role of inkjet printing, the thought is, why would you want to go to printed interconnections? There are a couple of important reasons to consider this seriously. One of them is the wire bonds, as are commonly used in many different applications. Obviously, they will bring some height. If we talk about a height in the area of 100 microns, it will become obvious that wire bonds will provide some hurdles for reaching that target. They are significantly above the 100 microns typically. So having solutions without these wire bonds help a lot. A second important reason in our experience is to have a complex process for making the interconnections. Think of chips with sensitive pads which can be easily damaged. Think about substrates which are delicate. It is pleasant that you not need to touch anything for making the connection work. This is where inkjet printed interconnections can help a lot as well. Other reasons why this is important could also be, for example, in reducing the number of process steps, in having less steps in the manufacturing process for getting the connection working. The picture here shows an example in which printed interconnections were made, illustrating what we said about the pitches. Here we have a chip, a memory chip, which is integrated. It has 56 micron square pads at 44 micron spacing. We could do it in a very thin way. We were able here to obtain a bare die with only 35 micron height, and it was mounted on a thin polymer film with 50 microns of thickness. Talking about the way towards applications, towards the realization of demonstrators and prototypes, how does that typically go? I would like to take you through the flow of steps that are typically made for this. The first important step is to select the optimal configuration for each application. It's important to notice there are no two applications the same. Every time we talk, we start with a detailed assessment about what exactly is needed in terms of functionality, what are the requirements, and how can we best make it. And that relates, for example, to the materials that are used, to compatibility requirements that are there, functionality, and it will also relate to how the circuitry can best be made. Typically, we start with feasibility step for doing that and making it clear. When we talk about the chip to be mounted in the circuitry, basically there are two options for putting the chip. Simply speaking, it is putting the chip with face up or with face down. And later, more details about what that exactly implies and what kind of opportunities that brings. Of course, the challenge always is to use very thin bare dies. If we talk about a low height, of course, we should start with the components. Chips typically come with a big package. As mentioned before, we have the wire bonds, we have, of course, the packaging material that brings quite some height. So the challenge is to find the appropriate bare dies. Experience shows this is a challenge. It's not simple to find the dies exactly as we need, but what I can say is that over the years, we have developed quite a supply chain that can help us very well with this particular challenge. Important considerations are, of course, also how can we verify afterwards that what we have done, what we have measured, is doing the job. I already mentioned the optical microscope in the beginning, and it's important to know other analysis facilities are available and used as well, if needed even up to electron microscopy. Going in more details about how we can put the chip in the circuitry, I would like to present two options with the face up and the face down. The first one is circuitry with chips in a flip chip configuration, so with the face down. The picture which we have over here is a view through a flexible substrate, in this case a PEN foil as well. What we see over here is printed silver wires. Of course, these were printed first in this approach. A chip with the pads on the bottom side. It has been positioned in an accurate way with the fine placer which we have at the lab. We used an anisotropic conductive paste for making the connections, and we're able in this way to achieve interconnections with a fine pitch down to 100 micron as targeted. This is one approach. I will also show the other approach and then discuss what are the pros and the cons of both directions. The other one, as mentioned, obviously will be with the face up for the chip. This is an approach which is very helpful in case, for example, we have a sensor or something which requires the chip to have the surface on the top side. Typically, we call this a 2.5D approach, and which basically means a couple of things. The first one is we make our circuitry obviously in 2 dimensions, and we try to keep the third dimension as small as possible with the low height as we talk about. Typically, the third dimension is created by bending the flexible circuitry in a certain shape. For example, the user interface of an electronic product, the smart glass, such kind of situations. The other height consideration, of course, is in the height of the chip. That's also what makes it a little bit three-dimensional. The chip doesn't have a height of 0. It still has some 40 microns left. And that implies that we have an edge on the die which is vertical and which makes printing over this edge impossible as it is from itself. This is why we have developed a process for making slopes which can help us to guide and to support the conductive interconnection over the edge of the die. We have done that in such a way that we have materials which is compatible with the inks, with the substrates, and which also is friendly for the chip itself. One of the nice things about this approach is that it enables a good alignment of the first chip. If this is the first chip to be placed in the circuitry, then we can control the location of that chip very accurately. So wherever location is very, very important in an application, there are clear advantages for this approach. Another important one, as mentioned, is it is very suitable for systems with the sensors face up, because it can be connected easily to the outside world. A few examples about how we typically proceed after having mounted the chips towards creating functionality. We have here an example of a demonstrator we have worked on. In this case, it was about a wireless IoT demonstration. The first challenge has been to realize a wireless capability in flexible electronics. In this case, we talk about a Bluetooth application where we had a printed electronics application with the circuitry printed, but also with the antenna printed, the curved shape on the top of the picture over there. We found a Nordic chip which is able to provide the Bluetooth functionality and can be obtained in a thin per die version. For this one, we found that the fan-out die first face-up configuration is the most appropriate one, and we were able to demonstrate and integrate this product in an effective way with printed interconnections. That was a starting point towards something which is more complete, because obviously if you can have the functionality of one chip, one of the big things you would want to have is the functionality of a couple of chips combined. So the next step, which I would like to highlight over here, is a demonstrator which had 2 chips. In this case, it was a combination of a wireless communication functionality and a touch functionality. Here we added to this Bluetooth chip, which I showed on the previous slide, a Cypress controller, which can also be obtained in a thin bare die way and which can control a touch process. The big white area on the left-hand side of the picture is a touch area. On the right-hand side, we see 2 chips. The bottom one is the Cypress controller, the upper one is the Bluetooth controller, and on the right hand, we see again an antenna. Here again, we have been able to achieve a very fine pitch for both chips, down to about 100 micron. Important to mention is, of course, we also need passive components for making a complete circuit work. In this case, we had components which still had a thickness of 0.5 millimeter, and of course, that puts a limit on the height which we can reach. In this case, the application came down to 700 microns, but be aware that we have a lot of choice in other passive components which allow a much smaller height. Having made such a circuit, of course, always the proof of the pudding is in the demonstration of the functionality. In this case, the device we made could be controlled with an app and could communicate with an app. And we show the examples of that on this slide. What I should say is what we didn't include yet in the circuitry is a battery. On the pictures we have over here, we see a separate PCB which includes a battery for powering the circuitry. Of course, a big challenge is to also include the power function on the flexible circuitry. We do have good experience with NFC for that purpose and are very interested in, for example, people and companies who are working on printed batteries. Here, basically showing the functionality implies starting the communication between the flexible product and the app in the smartphone and ensuring it goes in two directions. And as you would imagine, it did work as it should. We can touch the touch area, switch on the LED with that. That will be shown in the user interface on the smartphone, and the same thing will work in the opposite direction from the phone towards the circuitry. Just to show that this kind of printed circuitry with small interconnections can work and can do a very, very good job. What does that imply? And perhaps more importantly, what does that bring? One is that bare dies can be integrated using inkjet printed wire bonds. And a remark is we have quite a lot of possibilities in bare dies for realizing different functionalities in this area. Thin form factors down to 100 microns have been demonstrated and are realistic. And in this way, with flexible substrates, we allow a lot of applications, for example, in inmold, in smart glass, but also in many other areas like the wearables I talked about. Important for a lot of applications is also that we can integrate sensor chips in very thin packages with the sensor chip positioned in the right way. That brings me already to the end of this presentation. Of course, behind many of the things I told about, there are many considerations. There's a lot more we could talk about that. I'm happy to answer questions which may come up and also appreciate further contact if you like to hear more about this. Thank you.
Thank you very much for such an interesting presentation and for joining us today. Yes, please do leave any questions you may have for Arjan and we will take them here live. I have a question for you. Your presentation is about using inkjet printing for making interconnections with very fine pitches. Since the trend in the industry is that feature sizes are going down continuously, the resolution with inkjet printing may sooner or later bring limitations. What is your view on the perspectives for this long term?
Thanks for the question.
That's okay.
Well, the view is, well, there are many applications which can be developed with inkjet printing by itself. We see it's the beginning, let's say, of making printed interconnections possible, and we see a lot of potential for more applications with inkjet printing. But for sure, there will be challenges with the chips getting more complicated, the pitch getting smaller. Of course, we will reach limitations. This is why we also are actively looking and also involved with our company in next generation printing technologies. To mention one of them, the EHD printing is an important one. We see a potential for let's say further reduction of the scale down to, let's say, the single micron range. Of course, that will require considerable steps. It's a technology which doesn't have at all the maturity of inkjet printing, but it could bring the industry a lot further. So we're actively following that and also actively involving and exploring next generation printing technologies for making that possible.
Great, thank you. We have some questions from our audience. Do you formulate your inkjet inks in-house? Also, do you have experience with printing nanocomposites?
Actually, the answer to that is typically we do not formulate inks ourselves, but we have a lot of partners who are, let's say, able to make non-standard inks. And these include partners who are in nanocomposites. It's actually a very active subject at this moment to investigate in that area and to see what is possible with the printing. So if questions come up in that area, yeah, it's how to say it, it's short loop, let's say, to contact the appropriate partner and getting the right ink on board.
Okay. What kind of metals do you use for making the connections?
What kind of methods? Okay, it's mainly silver ink at the moment. We are exploring other inks as well, but I should say the vast majority is with silver inks.
Okay, thank you. And under what temperatures are the materials processed?
Ideally, it is 150 degrees thermal curing. We do have possibilities to do it differently, in particular with laser curing. As we see quite a few applications for which 150 degrees centigrade is too much already. Yeah, then we will check together with the customer what is possible, what let's say what temperatures are reachable, and how realistic is that with either approach.
Great. And this is another one. I missed this, but the interconnect was all based on silver ink? Question mark. Does it survive blending in a flexible hybrid system?
It does. To be honest, I should say lifetime, of course, is a consideration. It does survive blending, let's say, if that doesn't happen too often, if there would be continuous, or if there would be, for example, let's say hostile chemicals around, it would be difficult. Then it really would need investigation and perhaps also thought about encapsulation or about protection means, which could be helpful over there.
Okay, and another question here. What metallization do you prepare on the chip surface for electrical connection with inkjet printed tracks?
That is typically done per application, depending on what is possible in terms of chip supply. It's ideal is, of course, to have gold pads, but this we really need to check every time again what is possible and how to obtain.
Great. Okay. Well, we've certainly had some good questions there. I can't see any more coming through for the moment. So again, let me thank you. Thank you for joining us. Thank you for a super talk. I'm sure we'll see you in the Meet the Speaker session, which follows after the next presentation. And as I said that, another question's come in. What are the requirements to the carrier layer? We'll make this the last question.
To the carrier layer, that's it. That's it. Yeah, that's it. Basically, it's about compatibility with the ink. That's it. For example, it is stable, that the adhesion properties are good. Actually, there's quite a lot in the chemistry of the system in printed electronics applications. That's it. So what we typically tend to look to is adhesion properties. Is it friendly? Is it stable over time? What would happen upon stretching material? Will it, how to say it, guide the ink in a proper way and not damage it?
Great. Well, thank you. Thank you once again.